thanks for the invitation and thanks for coming. I come from Warsaw, so quite nearby. And I'd like to talk a bit about Akka and scalaz-streams and how these two compare. So there will be a couple of slides in the beginning, and then we will do some coding to see how it works in practice. Okay, so first, what is the use case for both Akka and scalaz-streams? So what problem are we trying to solve? I guess it's quite an important question, right? So there are various situations where we want to process data as it comes or in a streaming fashion, right? So it may be for various reasons. Maybe the data is too big to read into memory. Maybe it's a 10 gigabyte file and you don't have 10 gigabytes of RAM. Maybe the data is not ready at a single moment, so maybe it's coming like it's streamed over the web, or maybe it's continuously produced by some source. I don't know, maybe it's a stream of clicks on the website or something like that. So we want to transform, somehow process data in a streaming fashion. So the libraries I'm going to talk about today, they are designed for processing data in streams on a single node. Okay, so it's like more of a local computation. If you have too much data and you would like to distribute, if you would like a system which allows you to distribute your workload across a cluster of computers, then you should probably look at Spark. Which also has a streaming component called Spark streaming, but that's like strictly for multi-node computations. Here we are considering a single node scenario. Okay, so I guess if at any point you have some questions, just feel free to ask. Okay, if you don't understand something, or that's probably my fault not explaining it clearly enough. Okay, so how do the libraries introduce themselves? So that may tell us something about them. So first, Akka-streams is a library to process and transfer a sequence of elements using bounded buffer space. Okay, so that's like when you go to the website, that's what you can read, and you can see that the emphasis here is on the bounded buffer space. So when you are using Akka-stream, you can be sure that we are not going to overflow the buffer, so we are not going to use too much memory and end up with an out-of-memory exception. And we have the sequence of elements, which is our stream, right? In a similar fashion, we have that scalaz-stream is a streaming I/O library. The design goals are compositionality, expressiveness, resource safety, and speed. So we have some things in common. Resource safety, memory is one of the resources here. So we are sure that we are not going to run out of memory. We also have compositionality and speed, and in fact, when you compare the current speed of both of these libraries, they are both unoptimized, at least that's what the authors claim, and Akka-streams end up to be about 3 times faster in some scenarios, or 2 times faster in other scenarios, and we will see that as well. Okay, so let's move on. So like if you read the documentation more carefully, you will see that a common goal for both libraries is to provide compositionality. It's a difficult word. So what does it mean? So we are creating data processing pipelines, right? We want to process data. We want to process streams of data in some pipelines. And so what compositionality means here is that we want to build bigger processing pipelines out of smaller ones. Right, so we want to have like building blocks which we can prepare earlier and then reuse them to build bigger processing pipelines. It also can mean that we want to reuse a single small pipeline multiple times in various places. And so that's a common goal of both of the libraries. However, they approach it quite differently, as we will see later. Both libraries also aim to provide a type-safe API. How type-safe it differs. So Akka-streams is a bit less type-safe. So there are some places like merges and splits, which we will see also, which are checked at runtime. Scalaz-stream is like more on the extreme side. So everything is type-checked there. So if it compiles, it's like 90% of success. But then it's a bit harder to understand, at least for a beginner or for me. So both libraries provide quite elegant APIs to create, to define the data processing streams. And they like have a similar approach when it comes to actually designing the stream, okay? So the first thing you do in both libraries is you create a blueprint, okay? And that blueprint says, it describes how you want to process the data and how you want to transform the data. In Akka-streams, that blueprint is called a graph, and in Scala that is called the process. Okay, of course they had to pick different names. So that's like the first stage. You create a description of how you want the data to be transformed. And on later you execute that blueprint on real data, and that's when any work is really done, right? So at the moment when you create the blueprint, nothing happens with the data. Only when you execute it, the data is being processed. And in the case of Akka-streams, the graph is materialized, so that's when the data is processed. And in scalaz-stream, the process is run. Okay? So we are going to use these terms throughout the talk when we will see some concrete examples. Okay, so before we dive into the code, what are the components that build up a definition of a stream in both libraries? So let's start with Akka-stream. In a simple case, you have a linear processing pipeline, so you don't have any forks and joins. And in that scenario, there are like three basic building blocks that you are going to use. So the first is a source of data, and the source of data has exactly one output. Then we have a sink, which has exactly one input, and we have a flow, which has exactly one input and exactly one output, right? And these can be combined in an obvious way. Okay, so like a complete processing pipeline will consist of a single source, a number of flow elements, and a single sink. Okay, we can make it more complicated by defining arbitrary graphs, so we can split data and merge data, so we can have multiple sources and multiple sinks. But like the basic idea is that we have a source, some number of flow components, and a sink. Okay, so now that's when you create the blueprint. You combine these building blocks, right? And then you have to execute that blueprint as we said before. So when that blueprint is executed, so when it is materialized in the Akka terminology, so what happens, each processing stage is materialized into an actor which actually does the data processing. Okay, so that's that's where the Akka core comes into play. So you don't actually see these actors, but they are there. Okay, so each transformation stage that you are going to add will become an actor when the blueprint is materialized. And additionally to an actor, each stage materializes into a value. Okay, so for example, if we materialize a source, it will produce a future unit, and that future is going to be complete when the source is finished. Okay, if we have a sink which accumulates values in a variable, let's say it sums all the numbers it receives, that sink will materialize into a future int, which will be complete when the sink when the stream is finished and the sink has the final value. So in Akka-streams we materialize the graph, and each transformation stage becomes an actor plus a value which we can grab and actually get some output from this from the stream. It's very useful, for example, to wait for the stream to actually finish processing. Right? We want to know when the thing is done, if it's ever done. Okay, so one more thing about the blueprints is like having the blueprint is what gives you the compositionality, right? So you can materialize a blueprint many times, so you can run it many times, right, with different data sources maybe. You can reuse a blueprint in another context, so you can combine two blueprints and build a bigger one, and so on. Okay, so now that's the Akka side. Let's move to the scalaz side, okay? So in scalaz, we have a bit of a different approach. So over there, everything is a process. A process is like a super trait, and it has two type parameters which describe everything. So we have the first type parameter f. It describes the kinds of effects that occur when the stream produces values. And t is the t over here. T is the type of values that are produced by that stream. Okay. So, for example, and now we have various specializations of that definition. So, for example, we have process 0, which is a pure stream of values, right? And it's a type alias for process of nothing t. So there are no side effects when producing values, and we produce values of type t. Okay, so that's a stream. It's a pure stream of values of type t. We also have a process 1, which is also a pure stream, and it transforms values of type I into values of type O. Okay, so it's like a transformation component. We have a sink. A sink is nothing else. It's again a type alias. It's a stream of functions where each function takes an output value and does some side effects with it, right? So you can see here that it's a stream of functions which take the output values that the stream produces, and given an output value, it does some side effects described by the f parameter. Okay? So usually when we create a stream, for example, reading from the network or reading from a file, you will see that we get a process task string, for example, right? So that's a process which produces strings, and as a side effect, when producing these strings, we may have task side effects. So task is kind of a future, but better. Okay? Why is it better? It's better because it describes the computation that is supposed to be run. It's not a running computation in itself, and there are also some other points to that. Okay, so as I said, the process it is like a super trait, and it has several implementations. So like the whole processing of a process is a state machine. The state machine can be in one of 4 states. It can be in an emit state, which is the simplest one. We emit a value. It can be in a halt state, so that's the end of the stream. It can be in an append state, which means that the output of 2 streams should be concatenated or appended. And we have the await state, which waits for the completion of some side effects described by the type over here, and then produces some continuation of the stream. So scalaz-stream provides us with different combinators to create the stream descriptions. But then once we have the description, we pass it to a driver, and the driver is like interprets that state machine. So for any type of side effects that we want that can occur when evaluating that stream, we need a specific driver. So scalaz-stream comes with a driver which knows how to evaluate task side effects. Okay, and that's why you usually end up with task processes. So that driver, it kind of compiles that or runs that state machine and produces the output. Okay, so we will see how it looks exactly in a second. Now that's the last slide. So it's quite fashionable right now to be reactive, right? And both of these streams are reactive in their own way. So Akka-stream, like it's the most marketed reactive stream implementation, I guess. So Akka-stream implements the reactive streams standard. There is like a well, I'm not sure if it's a standard. It's like a common API that a couple of libraries implement. So what happens there is that when you materialize the stream, the data flows from the source through the flow elements to the sink, right? So it flows like in the natural direction where you would expect data to flow. Now, at the same time, when you create the data stream, there's a back channel created, and on the back channel, demand flows. Okay, so actually, when the stream starts up, no data is being sent, and only when the sink signals demand to the previous component propagates the demand all the way back to the source. The source, when it has received some demand from the downstream components, can send data. Okay, that's how the back pressure works. So the demand is signaled from the downstream components to the upstream components, and data is produced only when some demand is received. Okay, so now the demand, it's not like I want one element. It's usually the sink says I want 10 elements, so it asks for some elements in advance, right? So and this then the transformation component in the middle, it also asks for 10 elements and so on. So there is some buffering, right, at each stage. That's where the bounded buffer space comes into play. So thanks to the buffering, things can be processed in parallel, right? Each actor has some elements which it can work on in parallel with other actors, and that's called a dynamic push-pull. Now in scalaz-stream, you don't really have that. It's a strictly pull-based system, so elements are evaluated one by one. Okay, so elements are going only to be evaluated when the driver asks the stream for the next element. So like we don't have the parallelism here. Okay, we have to model parallelism explicitly, as we will see a bit later. Okay, so I hope that gave you at least a very vague idea of how these things work, and maybe showing this in practice will be more helpful. And just before we start, just so that you know who's talking to you. So as I said, my name is Adam Warski. I'm a co-founder and a coder at Software Mill, which is a software house operating in Poland, working remotely for clients all over the world. We aspire to be a trust organization, as Bruce explained yesterday. I'm working on a couple of open source projects, like Macquire and Supler for Scala, Inverse for Java, and some others. I have a blog and a Twitter account, so feel invited to visit. Okay, so the first example that we are going to look at is transforming a file. So I guess a quite common scenario is you have some text file, it's going to have some lines of text, and we want to run some transformations on it, right? And we are going to do it in a streaming fashion. Let's suppose that the file is really big, we cannot just read it into memory, and some of these transformation components may be slow, so we need the back pressure and so on. So we have a simple trait here, so we want to run the transformation. We have the source file, which is a text file, so there are some lines of text, and we have the destination file, okay? And we want to implement the same transformations in both Akka and Scala. Okay, so let's start with the Akka version. Akka-streams transform file, and we will implement our trait. Okay. So now we can implement this. So we are going to start with a source, right? We need a source of data. So we will our source is a file. So there's a synchronous file method on the source which we can use. So synchronous comes from the fact that behind the scenes it's using the old Java I/O API, not NIO2. That's why it's called synchronous. But as I said, that's going to be materialized into an actor, which will run like on a separate thread, like in the asynchronously, right? But the API that's used inside it is synchronous, hence the name. Okay, so if we look at what this gives us, this you probably can't see exactly, and it doesn't really show. Anyway, it is a stream, and it outputs bytes coming from that file. They are combined in packages of arbitrary length. You can't really say how long these packages they will be. These packages are wrapped into byte string instances. Byte string is like a better byte array in Akka, but it is kind of a byte array, just better for some reason. Okay, so the first thing we are going to do is we want to chop that bytes into lines of text. So we are going to add a transformation component, add a flow component, right? We have a source, now we attach the flow elements. So we will add a framing delimiter, and we will delimit by the bytes represented by the new line, right? And the longest we can accept is a megabyte. That's a very long line, but more or less. Okay, so now we have added to the source a transformation component which will chop our bytes into lines of text. Okay, so now we can run the actual logic. But that will again output bytes, so we have to turn the byte arrays into UTF-8 strings. Now we have a stream of strings, finally. So we have converted a stream of bytes into a stream of strings representing one line per stream element. So now we can run our transformations. So first we will filter out any bad words. So doesn't contain, and let's say that's our bad word, right? So that's looks very familiar if you work with the Scala collections, right? It's just calling the filter method, and it returns a new blueprint for the stream. Then we can map things, and we can replace in each line. We are going to replace each star with a 0. Okay, so now we want to write things back to a file, but before we do that, we have to transform this back into a stream of bytes, because that's the APIs that Akka gives us. So the first thing that we have to do is we have to put new lines between each two elements, because these were stripped out. Okay, so Akka-streams provides a kind of basic APIs only for processing data. It's like it's very easy to extend, but there's not much coming out of the box. For example, there is no operator to put an element between each two elements of a stream. So we are going to write that. So we are going to add that custom transformation component, and we will see in a second how to write one. We call it intersperse stage, and we are going to add the new line character between each two elements of our stage. Then we are going to map each string to a byte string, so we are turning things to byte arrays again. And then we are going to attach a sync, which will be a synchronous file sync, and we are going to put the destination file here, and I will explain what's that in a second. Okay. So now let's write the intersperse stage. Intersperse stage. Delimit or intersperse element will be a t, and is parameterized with a t, and we will extend stateful stage taken in t's and outputting t's. Okay. So we will need some mutable state in here, but it will be only hidden in our stage, and a new instance of a stage will be materialized each time we create or we materialize the stream. That's why we have provided a factory here, in fact, right? So each time we run the stream, a new instance will be created of that stage. So we will have a variable just so that we know if it's the first element we saw or not. Implement methods, initial. Okay, so there's like some API for defining stages. You don't really have to know it a lot. It's a lot of copy paste from the internet. So what we have to define in essence is the behavior of our stage when we receive an element, right? So we have received an element. So our transformation component received an element, and now we have to do something about it, okay? So first we will remember if that was our first element or not. Well, was first. So we store that. First is false. If it was the first element, then we emit downstream. We only emit the element. Okay. Otherwise, we don't. We emit two elements. Okay. We emit a list. Just should be lm of lm and no, first the interspersed element and lm, and we need to provide an iterator and ctx. Okay, so that's all that we need to do, right? So that's a transformation stage. It keeps track of information if it's the first if the first element of the stream already passed, and if it's the first element, then it just propagates it further. If it's the second, third, and so on element, it adds the interspersed element before it. Okay, so I guess that's quite straightforward. Okay, so now coming back to our example, we are not done yet. So you may wonder what's that keep right here. Okay, so as I said, when we materialize our blueprint, we get some values back from Akka, right? And here we specify. So here we have, in a way, that's a blueprint for a source, right? Because it is a source with multiple flow elements attached, so it still has one output, right? So it is kind of a source. So this source will materialize into one value, right? And here we have a sink, which materializes into another value, right? So this will materialize into a future when it's complete, when the source is complete, and this will materialize into a future when the sink is complete, right? And we are only interested in the value that the sink materializes to, hence we only keep the right value, okay? Okay, so that's our blueprint. So that's the blueprint, but as I said, we also have to execute it. So there's a handy method for that. It's called .run. And we are almost done. We also have to provide some implicit parameters. So the first thing we need to do is we need to provide an implicit materializer. In theory, you can have many different materializers. Here there's one provided which materializes the description of the stream into actors. And we also need private lazy implicit var system. We need an actor system created. So that's an Akka thing. It just allows the materializer to create new actors. So it defines a thread pool and allows to create new actors. And in the end, so that's the result. And the result will be a future. So we have to await for the results of the future, at most 1 hour. Hopefully we will be done by then. So the type of that is that's a future long, and the long is the number of bytes written to the file. So we just return that to the caller. Okay, and I have a test harness which needs a shutdown method. So I will just implement it right now, just for shutting down the thread pool. Okay, so that's the Akka version. So now let's write the scalaz version. Okay, it will be quite similar, although it will work quite differently. Okay, so let's write the scalaz transform file. Yeah, we implement the same trait. Okay, so the first thing to do is quite similar. We need to read the data from the source file, right? So there it was source.synchronous file. Here we have an IO object imported from a scalaz-stream. You probably can't see that, but you have to believe me, it's scalaz.stream.io. And it's an object with which we can create a new stream description. So we will read lines. Lines are read lines from the file. We need to pass in the absolute path. Okay. And now here the the API is a bit more rich than in Akka, so we immediately get the lines chopped by new line characters. Okay, so we don't have to transform the bytes, we don't have to do the framing and so on. If you go to that method here, you can see that it returns a process task string. So the output are strings, and and task side effects can occur when evaluating. The side effects will be, of course, reading from the file. Okay. Once we have read the file, we apply the same transformations as before. We can almost copy-paste code because it's the same. Although, like, we invoke the filter method, but of course it's a filter method on another class, right? But the name is quite obvious and it's the same. So then we replace each star with a 0. Now again, the API is richer, so we just have an intersperse method. So we put in new line characters between each two characters. Then we pipe that to encode the UTF-8. And finally, we attach a sink, which will be a file chunk, right? So here the sink, there is a source which read lines, but there isn't a sink which can write lines. There's only a sink which can write bytes. And here also there's a wrapper for a byte array. It's called a byte vector. So in Akka we have a byte string. Here we have a byte vector. Both are wrappers around arrays of bytes. So we write the to file. Okay, get absolute path. Okay, so that's again. Now we have created a blueprint. We have created a process which will do the transformation. Okay, it is a blueprint, so we can execute it multiple times. We can take parts of it and use it somewhere else. Like for example, like all of these transformations, they both in Akka and in Scala-z. Each time you call a transformation, you get a fresh process or a fresh graph, right? So you can take that the highlighted part, you can use it elsewhere and customize in any way. Like this, it's an immutable description of the process. Okay, so we have the description. We have to run it somehow. Okay, like in Akka, we have materialized things into actors. So the parallelism was kind of implicit, right? We didn't really see it, but in the background there were some actors created and everything was running in parallel, right? Here it's quite different. So unless we model it explicitly, there is no parallelism at all. And so to actually run this, we will run this synchronously on this thread that we are calling this from. So the first thing to do is called again run. But this doesn't yet run. This doesn't yet process any data. So the first run compiles the process description into a task, and that task, when run, will only do the data transformation. So there's a couple of variants. So we can run and discard any values that the stream produces. We can run log, which will create a list of all the values that the stream produced, which can be dangerous if the stream is large. We can run last, which will only return us the last value, and so on. Okay, so here, like, we write the file and we don't really care about the output value of the stream. It's going to be a stream of units. So we simply run. We get a task, which we have to then run again. Hence the double run. Okay, so we have run things synchronously, and when we run the task, here we have again a couple of options. We can run synchronously, so on the same thread, or we can run asynchronously on some thread pool defined by an implicit parameter. Okay, so that will be the run async. But here, like for testing, running synchronously is fine, and we have to return the length of the file written so that we can see that things actually work. So I have some tests over here. Okay, so maybe we will skip the 500 megabyte ones so that it's a bit faster, and we can see that things actually work. Transform file runner. Now Scala has to compile, of course. It always takes a while. And you can see that the Akka version should be about 1.5 times faster. So the limiting factor here is of course the I/O, which is similar in both cases. So yeah, from the warm-up you can see that 100 megabyte here took 5.9 seconds, and for Akka 2 seconds. Okay, so like it is quite a significant difference. Although the what happens behind the scenes is radically different, and the but the definition of the transformation itself is quite similar, right? If we so we can see the final results here. About 2.5 times, 2 times faster, more or less, right? So here we have like a synchronous computation in a purely functional way, right? There's a lot of things happening in the background. The reason why it's slower is that there's a lot of object allocation happening, just to keep things always immutable. And here again, the description looks quite similar, I think, like the API, but we have the implementation using actors. Okay, so now let's move to the second example, parallel processing. Okay, so here we get a list of integers, and what we want to do is we have some expensive computation, and we want to run that computation in parallel, so on two concurrent threads, on two parallel threads. On one thread we want to run the computation for even numbers, and on the other for odd numbers. Okay, so we want to split the stream into two streams, one containing even numbers, one containing odd numbers, and run the computation. The computation, as in all demos, will be very sophisticated. It will take a long time. It will be a thread.sleep, and yeah, let's see how we can model that using Akka and scalaz. So we have like a non-linear, right? So far we had a straight data transformation pipeline. Now we will fork and join. Okay, Akka-streams, parallel processing, makes sense, parallel processing. Right, so we have our input list, and we need to provide we need to produce a list of transformed elements. Okay, so the first thing that we will do in the Akka version is we will define a sink which will consume our elements. So like when we will be processing the elements, we will be multiplying them by 2, and then we want to combine the elements into a list again. Okay, so we want to get a list of all the results that were produced. So we will define a sink. We define the sink first because that's the value to which we want our stream to materialize. Okay, so we will do a sink.fold. We're going to fold it into a list of int, and the elements are going to be ints. Not surprisingly, so we are going to start with an empty list, and when a new element comes, so we are going to add elements to the front of the list, and then we will just have to reverse the list. Okay, so it's like a classical accumulation of results, right? We append elements as they come to the front of the list, and when the processing is finished, we reverse the list and we will have the results. Okay, anyway, that's just a sink which accumulates all the results from the processing. And we have defined it now so that we can materialize this stream into the value that this sink will materialize. It will materialize into a future of list of int. Okay? So now we will define a flow graph. So a flow graph allows us to define arbitrary splits and merges. So yeah, we will define our G will be our graph. So we are using the flow graph builder API. It's going to be a closed shape. So it's not going to have any dangling inputs or outputs, right? You can only materialize closed shapes, so which don't have any free inputs outputs. So it will be a closed. Yeah, we get an implicit builder and a sink. So The first parameter comes from the flow graph. It is a component which allows us to add new transformation stages, and that thing here corresponds to what we have passed here. Okay, the flow graph will materialize to whatever we passed as a parameter. So we have passed our sink, so it will materialize to a sink, to our sink that we have defined. Okay, so our starting component will be a source, and we will simply create a strict source of values from the input list, right? The in is the input list that we want to process. Now we have to add the splits and mergers as components, and then we will connect them together. So first we will define our split component. So we will use the builder to add a new transformation component which will split the stream into two streams. A new split root, and it's a thing you have to write. I will show it in a second. Given an element, if the element is even, then put it on the left, otherwise put it on the right. Okay? And the split root is implemented over here. So it's again, Akka's API is quite basic, but it gives you the APIs to create your own split roots. If I only can, yeah, okay. So the split root extends a flexi root. A flexi root can have any number of inputs and outputs. And again, it's quite simple. It takes a function which decides where to put the element, on the left, on the right. So the flexi root takes some parameters. So that's the input of the split root, okay, and that's the output. There are two outputs because there are two t's. Okay, here you can see that there are two t's. You can also have three outputs. Then you would use a variant with three type parameters. Okay, and they can be distinct. They don't have to be the same. Anyway, how the split root works. Okay, so here we have to take into account the back pressure and the demand signaling, right? So the split root will only do any work once there is demand from each downstream channel, because we don't know if we will put the element on the left, on the right. So we need demand from both downstream processing stages, right? So we have to know that they both can accept an element, right? So that they have space. So it says demand from all. We also can have demand from any and things like that. So we say that we want to have demand from both output components, and once we have that and we get an element, well, we run our split function on the element. If it's a left, we emit the element to the first output. If it's a right, we emit the element to the right output. Okay, so that's the part which is not type safe. You can see that I could put 100 here and it would compile just fine, right? Though it would fail at runtime, obviously. So that's the part that is not type safe. So we have our split component, and now we also will add a merge component. Builder.add. So that's built into Akka-streams. We don't have to implement it. It's simply a component which merges two streams into one. And like whatever element comes first is output first. And we will define our complicated processing function. So it will be a flow which transforms ints. And for each element, it will do a thread.sleep for 1 second, and then it will return the element doubled. Okay, so that's like the blueprint for our complicated transformation logic. Okay, so now we have all the components. We just need to connect them together, and to do that, we will do some ASCII art. That's what Akka allows us to do. So we will use some wiggly arrows which come from the flow graph builder API. So we connect our source to the split component. Okay, so the split component has one input, and we connect the source to that input. Then from the split component, we direct elements to our data processing stage, right? So we will double the element, and then this should go into the merge component, and we do the same on the second output, right? And finally we direct the merge to the sync. Okay, so you can kind of see what's happening here, right? It won't survive reformatting, but it looks nice. So like you probably noticed that I didn't mention which input and which output, so I could have written split dot out 0 split dot out 1. Okay, that would work as well, but like if it's used once, it automatically uses the next 3 input or output. And again, that part is checked at compile time, at runtime, of course, because there's no way at compile time to check that the shape of the graph and that connections are correct. Okay. Okay. So we have defined our flow graph, and now we can run it again. Implicit val system, actor system. Implicit val result, no, materializer first, actor material, and await dot result. We have our G is our description of our stream, so we run it, and when we run it, we get a future which is the result of the sync. And we will wait for maximum 1 hour, then we will reverse the results, as I said, because we are appending to the beginning of the list. Finally, system dot shutdown. Okay, so that's the API for creating flow graphs in Akka. I guess it is quite readable when you try to read the code what happens here, right? You can see how the data flows, right? That from the source it goes to the split, and that the split has 2 branches, right? Each branch does the same thing. However, when you materialize that, this will be created twice, so there will be 2 distinct actors, each running that logic. Okay, one for the left branch and one for the right branch, right? And that you then merge things together. Okay, so that's Akka. Let's see how it looks in scalaz, and here it's completely different. Scalaz streams parallel processing. Okay, we implement the same method. Okay. So as I said, scalaz-stream is strictly pull-based, so it will only do work when there is demand coming. So when the driver is trying to obtain the next emit state. Okay, and here it gets tricky with the 2 streams, because well, merging, there is a specialized combinator to merge 2 streams, and you can imagine that when you want to pull from either of these streams, you can wait for you can try to evaluate both of these streams in parallel and see which first emits a value. But then the split is really tricky, because you can't really well, you evaluate either the left or the right, and they should somehow compete for the source, right, to emit an element and then direct the element. So here we need to somehow model the concurrency explicitly. Because in Akka, like everything, like the concurrency is implicit, right? Everything is materialized to an actor, and obviously things will be run in parallel. Here we have to do it explicitly. Okay, so first we define our source, which will be a strict process of values. We can, just as we can create an Akka source, we can create a process outputting those values. So now, to do the split, we will have to model concurrency explicitly using queues. Okay, so we will have 2 queues, queue limit. The left will be an async bounded queue, and it will hold ends, the queue limit. The right will be the same. Okay, so we have bounded queues. The queue limit doesn't really matter a lot. 1 is a very safe value. Well, it doesn't matter a lot in this example. So we have created 2 bounded queues, and those queues will hold the elements that should go to the left or the right streams. Okay. So first, how do we put elements on that queue? Okay, so the queues give us some methods. So there's an enqueue method, which is itself a sync, right? So we can, I guess it's quite logical that an enqueue method is a sync because you can put elements to that sync, and they will be put on the queue, right? So it's a sync which accepts ints. And similarly, the write has the same. So what we will do, and that sync is remember that syncs are an alias for processes of, so as streams of functions. So it's like an infinite stream of the same function all over again. So what we will do, we will create an enqueue process, which will be a process with task side effects and producing no values. It will just enqueue elements on the queues. So what we will do is we will take our source, we will zip it, so we'll create pairs with the left.enqueue, and that itself will be zipped with right.enqueue. So what we will get here are triples. The first element is a number, the second is a function to enqueue the element on the left queue, and the third is a function to enqueue the element on the right queue. Right? So once we have those triples, we can actually do our splitting logic. Element enqueue. Enqueue is a very difficult word to write correctly. Okay. If the element is even, then we call left enqueue on the element. Otherwise, we call right enqueue on the element. And what we get now, so this returns a task which will actually enqueue the element, right? It is a task, so it is a description of how to put the element on the queue. So now we get a stream of tasks. And given a stream of tasks, we want to flatten it to a stream of the values that the tasks produce. So there's an eval method for that. So this flattens a stream of tasks into a stream of values. And on complete, we need to also close the queues. So that's just some resource management. So when the start, when we have unqueued all numbers, we want to close both queues. So that's just something that is needed. It's not crucial to understand what's happening. So you can just about that. Okay, so that's our enqueue process. Now we will define our processing function. Given an element, we will create a task. So there we have created a future. Here we create a task. Thread.sleep. So that's the same logic. Element times 2. So that's all the same. Okay. Now we have a process to put the elements on the queue. Now we need some process to actually transform the elements and combine them together, right? So we need a dequeue process. So the left dequeue, we will take the left queue. We take the dequeue, which is a stream of ints, right? When you dequeue things, when you dequeue elements from a queue of int, you get a stream of ints, right? Which is finished when the queue is closed. So we dequeue things, and we eval map this using our process element, and we do that the same on the right thing, on the right side. Okay, so now we have the enqueue process and we have two dequeue processes. And to actually run things using scalaz-stream, you need to have a single process which does both, right? Like whatever is ready. So what we will do here is we take the enqueue process and we it. Oh, I didn't create the dequeue process yet. So the dequeue process is going to be the left dequeue merged with the right dequeue. Okay, so merge is an operator that takes two streams and merges them together. Okay, and this works because when you try to pull from the merged process, right? What happens is they try to pull from both of the streams that are merged, and whoever returns an element first wins. But so we have an enqueue process and the dequeue process, right? So now we need to combine these together to actually run everything. So we use the enqueue. Y is like a specialized merge where you can say which elements you want to keep and which elements you want to discard. So we will merge this deque is even a harder word. We want to merge this with the deque process using y either, and we only care about the left elements, or the right elements coming from the deque. Okay. And so now we have the description of our process. So I guess that's quite tricky to understand, and it took me a while. So what is happening here? We have a stream of units essentially, and that unit, each unit corresponds to enqueuing an element on a queue, right? Now, to run this, we also combine this with the deque process, which produces our ints, which are the processed ints, right? So we want to run these two concurrently, right? The enqueue with the deque, right? So they will so obviously first the enqueue will run, then the deque will run, then the enqueue will run, and so on and so on. But we want to run these concurrently, so we want to merge those two streams, right, into one stream. So when the driver evaluates our streams, it tries to run both streams, and we only care about the elements created by the right stream, which is our deque stream. Okay. So now we get a process, like a blueprint, so we can run it. This time we will run log, so we want to get all the values output by the process. We get a task, which we can finally run. And, okay, let's try uncommenting this. Again, it's a small test harness. This should run using the same, in the same time. Run to list is missing. To list, okay, because it probably returns an iterable or something like that. And you can see that the run times are more or less the same, right? We have 5 elements, so it's going to take 3 seconds to process them all, right? Because we take a second on each pair, so they're like 2.5 pairs. And you can see that it's like as you would expect. Here in Akka, it just happened so that the right processing was faster than the left one, so the first two are swapped, right? And so this works as expected. Okay, so I'm almost done. I have 3 more slides. So first, I have shown like the basics of both Akka and scalaz-stream, but there are like whole ecosystems growing around these two libraries. On the Akka-stream side, there's Akka-HTTP for defining REST services, which is built on top of Akka-streams. There's Slick, which you can with which you can connect to the database and also get a stream of values coming from the database. And they promise that it's going to be optimized in future releases. On the scalaz-stream side, there's like a parallel ecosystem. There's, for example, HTTP4S, which is the Akka-HTTP counterpart, is for defining REST services where you get processes, like from the, when a client connects to your API, you get a process, so a stream of bytes coming from the client, and you get a stream of clients as well. You have Doobie, which is a library to connect to the database and again get a stream or a process of values coming from the database. There's also a rewrite happening of scalaz-stream, which is called FS2. So it's going to be like the next generation, and it's going to be scalaz independent because of political reasons. There are also other streaming libraries like Play Iteratives, which is like the original one, which is now being deprecated in favor of Akka-streams. There's RX Scala and there's Monifu. Okay, and I have some stickers, mainly Scala time stickers, which is our Scala newsletter. So if you would like a sticker, just come to me later. And all of these slides are over here, if you would like to take a look. And there's also some more examples on the blog I wrote some time ago. If you want, there's 3 or 4 more examples. And yeah, I'm here for the rest of the day and the party, and I guess I ran out of time. So if you have any questions, just come and ask. Okay, thank you very much.